Anyway, there's like all sorts of consideration with routing and networks. I really enjoy routing. For MANETs, what you typically do is something called like mobile ad hoc networks. So anyway, so going back to, again, I like getting back to the things I said I was going to go over, and I was like, oh, what? And so we were talking about linearizing these graphs, like getting topologically sorting this graph, and I'm like, what is he talking about? It has to go and turn it into it's linear time, but I totally missed this bit. O of m plus n. That's linear time for a graph, where number of nodes and number of edges, right? And it all just had to do with the way I was structuring it versus the way that it should be structured. So the way I was structuring it is that you check, right? The algorithm for finding this is find the node with no incoming edges and order it first. Delete it and recursively compute a topological ordering. But the idea here is that if you want to be efficient about it, right? So this node is the node with no incoming edges, right? This node over here is the node with no incoming edges, right? This is our first thing in our topological ordering. Once we remove this, one of the nodes that it pointed to, one of the three nodes it pointed to, only those nodes could possibly be now a node with no incoming edges, right? It could be something like this. But only one of them could have no incoming edge. Make sense? Because it has to be directed acyclic. If they were all pointing to each other, it would be a cycle. So you only have to check the nodes that you're attached to, and since you're only checking the subset, you're checking every one of the edges. So you go through every one of the nodes and check all their edges. It's n plus n time. That's why. I was just simply rechecking the whole thing, which was wasteful. So there you go. Can be in linear time. Just requires a bit of a bit more thought. So okay, paths. So we've been so you've done this before, paths. You've done Dijkstra's. It's like it's mandatory from here until you're done studying computer science, which is that whenever you're introduced to a class on graphs, you have to learn Dijkstra's algorithm. You'll soon find that the hardest part about Dijkstra's algorithm is actually spelling his name. By the way, I should also point out, check out some of his handwritten papers. He has great handwriting. It's like amazingly good handwriting. Okay, so we have these two problems, right? First off, the last chapter about graphs, we were introduced to DFS and other things. DFS could help us find out, given two nodes, is there a path from two nodes? Here we're going to be talking about what is the shortest path. Shortest path is useful because short can be least energy, least money, least effort, whatever. So the distance between the two nodes is the length of the shortest path between them. Application Erdos number and Kevin Bacon number, as well as your Erdos-Bacon number. I should probably explain what those are. There's an idea here between about 6 degrees from Kevin Bacon. The idea here is that every actor is at most 6 steps away from having acted with Kevin Bacon. So your Bacon number is 0 if you're Kevin Bacon. If you've acted with Kevin Bacon, your Bacon number is 1. If you've acted with somebody who's acted with Kevin Bacon, if you've acted with somebody whose Kevin Bacon number is 1, your Bacon number is 2.
I think we talked about this. Who's Kevin Bacon?
Excellent. What we'd expect, an actor. Okay, Erdos number is similar. Paul Erdos, who was a very prolific mathematical publisher. Basically, your Erdos number, if you published with Erdos, your Erdos number is 1. If you published with somebody of Erdos number 1, your Erdos number is 2. My Erdos number happens to be 5, which seems to be the average for anybody who has an Erdos number. So, if you want an Erdos number, publish a paper with me, I guess. An Erdos-Bacon number is the lower of your Erdos number or Bacon number if you have one. Fewest hops in the communication network, obvious applications for these things. Depth first search is not good for finding your shortest path because it's good for like doing kind of maze stuff, going through stuff and backtracking. It's good at producing long winding paths. You use that if you want to try to navigate stuff and try to check stuff off. So it's great for getting through mazes. On the other hand, if you want to find your shortest distance, you're pretty much using either breadth first search or a variation of it, right? And you've all learned breadth first search, where whereas depth first search uses a stack, breadth first search is going to use a queue, right? Right. All right. So let's go ahead and try programming that out, just as a nice warm up, shall we? Bit more interesting to program it, right? Okay. So what we're going to do is that I'm going to call this BFS. I haven't done this in Python before, but I've done it in other programming languages, so shouldn't be too bad. Import network X as NX, right? So that's going to give me, let me just go ahead and run that and make sure that I am actually doing the import right. Well, it didn't crash and burn, so yes, it says good. Okay, next what we're going to do is that we are going to create a def BFS, which is going to take in a graph G. And the other thing for graph, even though they don't say it over here, actually it does say it. We want to take in a starting point, an S. We typically use, so by convention, by the way, and this textbook breaks this convention, unfortunately, a lot of the time, and other textbooks do. But when you're dealing with nodes, I always like to use strings for my nodes. Like, I like to use like labels, like A, B, C for the nodes, because the edges can have weights, and those weights have numbers, and it gets a bit annoying when you say the distance from 2 is 2. And it gets a bit, so that's what I'll be doing that. So S typically is your start, D is your destination or your finish, so you use either D or F for your last point, okay? So the next thing we're going to do is that we are going to do a queue. And I'm just trying to remember the best way to implement a queue in Python. I know you probably want to do it with a list. Okay, and I know you can append and you can pop, but that's useful for stack. Let me go ahead and look that up. Queue in Python, because you can do it says a synchronized queue class. No, and I don't. And again, I don't want it in Japanese. I want it in. Let me just go ahead. Can I do that? Does that work? Yes, queue. Okay, so it's a queue. Boo. Okay. So whatever. We will just simply use a list as a queue, and we can always replace it later. Okay. So next, what we're going to do. So we need a queue for keeping our nodes, and what we're also going to do is I'm going to use create a set called scene. This will keep track of everything I've seen, so I don't go and re-add things, if that makes sense. Okay, and then what we can do is that we can, let's see, how does our algorithm want to output it? It wants to, for all vertices reachable from S, the distance to U is set to the distance from, okay. So we want to make a dictionary as well. And then we're going to create a dictionary called distance, where the key is going to be the node and the value is going to be the distance to that node. Make sense? Okay. We are going to return the distance. Okay. So now, and I'm going to save this and close this, and I'm going to open this up in VS Code, because VS Code is going to give me a lot more hinting, if you know what I mean by that. Do you know what I mean by that? Okay. Okay.
Use PyCharm.
I could use PyCharm, but that's over. I feel like I use IntelliJ a lot, so PyCharm, so I feel like I just get a bit too much in. I don't need everything PyCharm has to offer. I don't think I do anyway. Okay. So now we haven't done this with NetworkX, so this will be useful for you. So let's go ahead and put queue.append actually it should be q dot insert 0 s scene dot add s. We've seen our source. We want to put our source in our queue, right? And finally, what we want to do is we want to, now this is going to be horribly inefficient because our queue is basically inserting to our queue. It takes O of n time, but that's okay for right now. We can always replace it with a real queue later on. And the next thing we want to do is ds is equal to 0. Or we should say clock. Let's go ahead and move it over here. Clock is equal to 0. Let's see. Just trying to figure out the best way to implement the clock. Oh. Okay. Let's see. So we don't need a clock, we just need 0. Okay. Okay, so ds is equal, this is going to be the hardest part for me to figure out, which is doing the distance. Okay. Now, for, so let's go ahead, while list, so while's queue, length of the queue is not equal, it's been a while since I programmed in Python. Or rather, a while since I programmed like doing data structures like this in Python. So while length of queue is not equal to 0, while we've still got stuff in the queue, what are we going to do? We are going to queue dot pop, which will get the last index out. We'll say that's current. And then we want to do graph. Graph is equal to, so let's go ahead and look up what the graph operations are for graph, network X, because I want to get the neighbors of something in a graph. Okay, good thing we're doing def for search first, because, and again, for one of your programming, like one of your problems, you're being required to work with network X. So this will probably be a good reference for how to do that. Tutorial reference. Okay, accessing edges and neighbors. So, okay, graph, we get a graph. So for fast examine of all nodes, so let's see. For n neighbors and adjacency items, so node attributes. Boo. Why are you being so annoying like this? Graphs. Neighbors. Okay, return to, oh, there we go. Neighbors, and that is, sorry. I'm just trying to figure out the best way to do that. Let's see. G dot neighbors. Let's see if that works. Of current. Okay, for some vertice in the neighbors, if v not in scene, if it's not in our scene set, then we add it to our scene. That is the issue with typing and talking. Scene.add s, not s, current v. So for every neighbor of the current, if we've not seen the current node yet, we add it to, sorry, if we've not seen the neighbor of this current node, we add it to scene, and then we go ahead and we do q dot insert 0 comma, v. We insert it in. We'll figure out distance later. Okay, we will print out scene, return dist. Let's go ahead and create a graph. Graph is equal to graph is equal to nx.graph. Okay, and g.add edge 0. Let's go with A to B. B to C. And B to D.
Is there like a automatic method?
It probably is.
Does like exist
Well, let's go ahead and see BFS from G to A. Let's see what happens when I run this. Okay. It says B, A, C, D. I'm not really sure why. I'm telling it to do from A, print C, but it's visited all of them. It's visited all of them, and it stopped, which means that this function works. I wasn't sure if that was the right syntax, but fortunately, a lot of libraries in Python operate on the principle of least surprise. So that is good. Okay, so here is the question about like how do we keep our distance up? So for all the edges, if the distance is currently infinity, inject into the queue. Okay, and then our distance is equal to the distance. Okay. And so dist is equal to, the distance to V is equal to the distance to the current. That's simple. Plus 1, right? Well, the distance of, so now that should be done, and let's go ahead and print what we get out from that, which should give us 0, 1, and 2 2s, right? Because the graph goes from A to B, and then B goes to C and to D. So there you go. We've got a working breadth first search. Okay? Now, if we actually had properly implemented a queue, as opposed to just using a list, because again, this is an array list, so we were inserting at the beginning. So whenever we're doing this operation, it's rather expensive. Python doesn't really do a stack because it just uses an array list for that. And then it's got its cube, but whatever. And again, this scene over here is to make sure that we're only interacting with things we've seen before. The distance is what we care about. Okay, now breadth first search is basically as good as it gets when it comes to doing, it's as good as it gets when it comes to doing undirected graphs. Unweighted graphs, I should say, because every length has the same length. It has n plus m time, right? Think about it for a second. You start at every node, and then for each one of those edges, so it's the number of nodes plus the number of edges. That's the runtime. For each node, we travel along the edges to each of those nodes, and then for each of those nodes, we travel along the edges to those. So every node gets visited once, every edge gets checked once. Assuming that it is fully, assuming that we're talking about it, assuming that our graph is fully connected. If it's not, it's going to run slightly, well, actually, if it's not connected, it's still big O, because a big O is the upper bound. It just won't be big theta. All right? So, on the other hand, again, what makes breadth first search a bit boring, shall we say, is the fact that we have everything is the same length, right? And so you know that now that Dijkstra's is a way to do that. Although, actually, we do have an even dumber way of doing, of figuring out what the shortest length is with weights than doing Dijkstra's. It's like dumb, but it's smart, okay? So here's the edge length, right? Here we go. We've all done this before. Shortest path applications, basically everything. Okay, optional truck routing, map routing, seam carving, robot navigation, typesetting in LaTeX, oddly enough, scheduling. Okay, we can we can use a hash table using the weight of the edges to store the wedges, so we can just like create a reverse lookup of those edges. But here's a pretty fun trick that you can do, a simple trick you can do rather than doing a routing algorithm like that, which is that you just simply insert like virtual nodes into in between each of them. So notice that C to E, it still has a length of 4. B to E, it still has a length of 3. All we've done is we've turned it into an undirected graph with these like phantom nodes in it. Of course, that doesn't really work so well if in this case, right? It works well for some other things, but it can take quite a bit of time, right? So it's a simple trick though. It's like one of those useful tricks, thought experiment things, but otherwise not really. So Dijkstra's, right, the way that you've learned how Dijkstra's works, right? What we do with Dijkstra's is that you kind of have this this pool of nodes that basically have already been explored. What you do is that with the pool of nodes you've already figured out the lowest path for, you look at all the nodes you can connect to from that and say, okay, I'm going to add this node to the pool of explored nodes, that node being the cheapest one. You repeatedly choose the unexplored node, which minimizes this. Why do they bother writing it in such horrible mathematics? This comes from the other textbook that we don't use, the Corman book, I think, that notation. You choose the edge such that it minimizes the distance to there, blah, blah. You know how it works. You've done Dijkstra's. Okay. We don't need to prove it's correct right now, but the question is, how long does it take? That's the big question for Dijkstra's. So let's go ahead and actually run Dijkstra's for a second, on a random graph to figure out how long it's going to take. Let's go ahead and grab. We'll just choose this graph. I'm literally choosing a graph at random. It does not matter for the sake of this argument which graph I am using. Okay. Oh my God. Why is this? Okay. So let's go ahead and figure out the shortest path from A to everything else. Okay. Because there's a reason I'm not implementing this yet, because it matters. It really does matter, because we've only ever solved this abstractly, and now we got to start thinking about the practical implications of this. So the classic way we do this is that here we list out we list out the nodes A, B, C, D, and E, right? Okay, and we say it takes 0 to get to A because that's our starting point, and then so we have a D and we have a P. D for distance, P for predecessor, right? We set everything initially equal to infinity, right? Okay, and we say initially we can get to everything from A with an infinite cost. Then what we do is that we look, so how do we choose the next node, right? We look at each of the ones and go. Well, what we do is we start out with A, and we apply its edges, right? 1 and 2. Okay, we're done with A. So now what we do is that we actually get into the bulk of the algorithm. We repeatedly do the following. We look at the edges that are remaining, sorry, we look at all the nodes, choose the one that's remaining that's unexplored, that has the lowest cost to get to it. So that would be C. So now that's explored, and now we explore from C to go to other places. We can get to C to B, and that's equal to 2, but we already have 2, and then C to E, that gives a cost of 4. Sorry, C to E is an additional cost of 4, so total 5. 5 is less than infinity. We put down 5. We put down, how did we get to E? We put down C. Right? Next, we go to infinity 5. We choose B, right? So we're going to choose B. And then we get B to D. Right? We've seen this before. Okay? I'm not going to even bother finishing it. So the question is, I was going through these 5 nodes to find which one has the cheapest which one's the cheapest. How long does that take me to do? Well, with the naive approach that I'm just describing, I had n nodes, and then I compared n minus 1 remaining nodes, then I looked at n minus 2, then I looked at n minus 3, then n minus 4 nodes. That way, the way I was doing it goes n squared. So for a grand total of, for Dijkstra's algorithm, right, for each node, so what I do is I look at each node. I believe it comes down to, if I'm recalling my math correctly, the way I've just described doing it is v squared plus E. So the number of vertices, right, squared, because I'm going through and choosing each of them. Then I've got the number of edges, right? Let's go ahead and see what Wikipedia's runtime is for a second, okay? As if I didn't know. Like I said, the hardest part about Dijkstra's is spelling his name. Okay? Let's see what Wikipedia says his algorithm is. Oh, it's E v log v? What? Wait, Dijkstra's original algorithm does not use a min priority queue and runs in time theta v squared, where v is the number of nodes. What happened to E? Why is there no E in there? What is the upper bound for E? The upper bound for E is going to be O v squared, right? Because the most edges that can exist on a simple graph are v squared edges, one for every possible pairing of nodes. So hence why that's just simply dropped there. Okay, shortest path, so that gives us an upper bounds for basically shortest path algorithms, which is v squared is basically as bad as it gets. But if you use a priority queue, you can drop it down. Specifically, they say we're using a Fibonacci heap. Okay, so do you remember what a priority queue is? Or no?
A queue has a priority.
Yep, priority queue. It's a separate data structure from a queue. A priority queue is basically the easiest analog is triage, if you know what that is. So triage, when you go to a hospital with an injury, the first thing they perform is triage, where they assess your injury. Heart attacks need to be seen immediately. Head wounds probably are severe. Broken fingers, painful, but they can wait. Triage, basically sorting people into people who are going to die without immediate attention versus people who can wait. You will now, right? If you're waiting at the hospital and you've broken a limb, it sucks. But if a person comes in because they had a heart attack, it doesn't matter how long you've been waiting for. If you're still in the waiting room, that person's going to cut ahead of you because they have a higher priority. Make sense? So that's what a priority queue is. It's basically saying that everybody who's on the kind of the same level is going to be whoever's, if the person, if you all have similar injuries, whoever's going to be whoever's been waiting the longest will be seen next. But as soon as somebody comes in who has a higher priority, that person is going to cut in front of you no matter what. That's what a priority queue is. It basically moves most important things to the front. Now, the way a priority queue is typically, we teach priority queues in data structure is the following. We use a binary heap. Do you remember binary heaps?
Oh, yeah.
Min heaps and max heaps, right? And the difference between them is whether we consider high numbers to be high priority or low numbers to be a high priority, right? Which should be next? The low numbers or the high numbers? Doesn't matter. It's all the same. Doesn't matter min heap versus max heap. It's just a philosophical difference there as to whether of how you want to do that. Okay. So binary heaps, right? If you remember, what are the operations for, if I've got a binary heap here, 5, 7, and it's going to be a min heap. So 5, 7, 12, and let's do 10 and 8, right? It doesn't have to look like a tree. It doesn't. So first off, binary heaps, they're complete trees, right? Do you remember what that means? They can be perfectly embedded into an array. Like this, 5, 7, 12, just left to right. They can be perfectly embedded in an array. There's a formula. You don't actually need a node structure. You can just use a formula to figure out who's your child, which is pretty nice. It means that it's nice and... All right. So now let's say I wanted to add this node, this item back in, just a review. What does that mean if I want to add one in? That bubbles up, right? So say I want to add this node to a binary heap. Do you remember how that works?
We do exchange with 12.
Yep, you exchange with 12. You exchange 1 with 12.
Then exchange
And then you exchange that 1 with 5. So that, because the way I like to think about it is that especially with min heaps, is that these are weights. These are literally weights. The lighter items bubble to the top and the heaviest items sink. It's a very easy way to think about it. Okay? Now, how long did that take? It took 2 swaps essentially. 3 operations, let's call it. 1 to add, 2 to swap. Okay? Or you can look at it as 3 checks. I did 1 check here, 1 check here, and then 1 check to see that it was at the top. Okay? In other words, your operations in a binary heap are all going to be log of n. LGN for log base 2. Okay?
which is high.
Sorry?
Which is high.
Hmm?
The height of the tree.
Yeah, the height of the heap. Yeah, or the height of the heap, because it's a complete thing. So it's never gonna be unbalanced. Is the idea? It's never gonna be unbalanced. Heaps are pretty cool like that. But those are not the only implementations of a heap. And in fact, the idea here is that with Dijkstra's is that rather than stuffing all of these, what you'll do is rather than keeping these in a table that you keep iterating through, like I was doing, you keep this table as a heap. So as you go through and adjust the items, the weights update and they change in the priority queue. So then when you dequeue, it just takes log n time rather than going through O of n for the entire thing. Hence v log v. Now, although it gets a bit tricky because again, how do you update this thing? But let's go back to our slides for a second. Okay. Right. Over here, right, Dijkstra's was using, and the original one Dijkstra was using, it was unordered array. It took constant time to put something into our queue. It took the time it took to get something out of our queue, okay, to figure out what the smallest item in was O of n, where n is the number of things left in the priority queue, if we're using an unordered array as our priority queue. A binary heap would do log n, and if we use a binary heap, we actually get that time down to m plus n log n. So m being the number of m is number of edges, n is number of nodes. Hey, don't do that to me, right? D-array heap, right? So what is a D-array heap? Well, binary is base 2. If you use like a base 4 heap, you can get that log even smaller. But even better, if you use a Fibonacci heap, you can get this runtime where the log n to delete something from it is log n amortized and decreasing the key, which is going through and changing the changing I believe that is the change a key operation. So right, remember what I was saying where basically you have to go through and change the weight? It takes log n. Here saying you can do that in constant time amortized.
What is amortized again?
So amortized again is that like with array lists, where typically if I add to the end of array list, it's constant time. And we like to say it's constant time or amortized because if you add 1,000,000 items to the array list, on average, those O of n costs that you get from adding an item to array list and then having it to reallocate, that cost of O of n gets spread out among a lot of your additions. So basically it's saying, if you do this a bunch of times, I can safely say the average is constant time. And similar like with a hash table, you can say almost all of our operations are going to be constant time, with high probability and over most of them. So again, binary heap, we went over that. D-array heap, that just generalizes a heap. Fibonacci heap, let's go ahead and go into the textbook about this for just a brief moment. Again, I skipped through a lot of stuff here because, again, the proofs I can always leave for another point, but we see how it's efficient and what it is. We ran through it and we physically saw what the runtime would be. And again, you've done Dijkstra's. I don't feel a need to belabor the point. Okay. Yes, it says, we will say little of except to mention a curious feature of the time bounds. An insert takes a varying amount of time, but are guaranteeing to average over the course of the algorithm. So it basically, your book barely even touches on what a Fibonacci heap is. That is how it is a complicated data structure. If we actually click on Fibonacci heap over here, it says that it's got a weird structure like this. It's a collection of trees satisfying the min heap property. That is, the key of a child is always greater than or equal to the key of a parent. And so the minimum key is always in the root of one of those trees. Weird. And it probably has something to do with the relationship between Fibonacci numbers for his stuff, but that's fine. Point being is that understand that it is a complicated data structure. It is fairly recent as data structures come along, 1984. So slightly older than me. But the idea here is that these things, Dijkstra's algorithm has been around for a long time, and there's still, abilities. It's still room for improvement on it. That being said, we talk about, and what we'll do and cover next time is the stuff that you haven't covered, right? Sorry that I spent so much time on stuff that you've already covered, but you haven't covered the runtime, I don't think, for Dijkstra's like this.
Yeah.
And more importantly, the Dijkstra's failure case is actually pretty darn important, right? Which is Dijkstra doesn't really do well with negative cycles or negative edges. And what I mean by that is take a look at this graph, right? So we've got A, we've got D, we've got B, and then we've got C. All right, this is a cost. This doesn't matter what the cost is. I'll put it at 20. Okay, the cost from A to D is 20. -1, -20, +20. In this graph, there is no shortest path you can't declare a shortest path to D in this case because there is no shortest path because of what we have here is a negative cycle, right? We have a negative cycle in this graph. Dijkstra's here won't be able to give you an accurate answer because I can always just go in and say, and I go one more time around the cycle. If going around the cycle ABC produces a net result of -1. Going around it again would give me -2, -3. So I can go around it infinite times and kind of build up infinite negative whatever I need. So the shortest path from A to D is whatever the heck I want it to be. Or more accurately, it's invalid. All right. So, okay. And so what we're going to see on Tuesday is we're going to look at Bellman-Ford. And what Bellman-Ford does is that it basically says we're going to do that update operation on Dijkstra a lot more times, which means it's going to take longer. But the end result is that it can't like, solve this problem. It's not a solvable problem, but it can at least tell us that we can't trust any answer we're getting out of this because it's got a negative cycle in it. Does that make sense? Like Bellman-Ford will at least be able to tell us this will not work. Okay, that's what we'll go on. Now, before we fully close up,